Now, we're going to start our vodcast on types of reactions in kind of the middle, so please go to Roman numeral 3 in your PowerPoint notes. And we're going to take a look at what kind of information can be provided in an equation, understand and define some symbols, and then talk about the 5 basic types of reactions that we recently learned about in class. Please note you have a quiz on the symbols and anything in the first section of the chapter 10.1 on Tuesday. So equations can act as instructions, and those instructions will help describe both the process, who are the reactants, who are the products, what are the amounts, we'll do that in another chapter, and how can you relate the molar ratios of different substances to each other. It can also tell you about energy changes, and we've learned some terms recently about endo and exothermic. Now we're going to begin to define them officially. So delta H stands for change in enthalpy, a fancy word for heat. And it's the amount of heat energy released or absorbed, in this particular case, in a chemical reaction. So as you saw on video, you can burn hydrogen in the presence of oxygen to make liquid water. And that process will release 286 kilojoules for every mole of hydrogen that you burn. Please notice that the number is a negative number, and a negative sign simply decides or tells you which direction energy is flowing. In this case, from the system, the burning of the hydrogen, out into the surroundings, anything outside of that defined system. You also learned in the past that a reaction can be endothermic, and you saw a short video showing that you can take water in its liquid form and decompose it into hydrogen and oxygen gas. Well, that took energy, and so now our delta H for the reverse reaction will be a positive number. It takes 286 kilojoules to break or decompose water into its constituent gases. So whenever you see a delta H off to the side of a chemical reaction, it's telling you if a reactant is endo or exothermic, which way the energy is flowing in or out of the system, and also the amount of energy required per mole of substance. Now there are many symbols that can also give us information about chemical reactions, and they can specify a number of things. If you see a little S, or it should be CR, not just C, to the bottom right of a substance, that stands for the substance being a solid or crystal. You already know L to the bottom right means your substance is a liquid. You've learned that G stands for a gaseous substance, and AQ, or aqueous, means that something was dissolved in water. So those are fairly common symbols that tell us what is the form of matter, either on the reactant or the product side. Now it's a little hard to see, but on number 5, this is an arrow. This is representing the yields arrow that you would find in the center of a reaction. And in this particular case, it's telling you that that reaction took place under a certain pressure. We'll learn about pressure in another chapter. It's measured in kilopascals, and this is saying that this reaction took place under a lot of pressure, 1 times 10 to the 8th kilopascals. Now, of course, if you put the symbol of temperature above an arrow, that means that this reaction took place at 0 degrees Celsius. Or if you put the symbol of an element above an arrow, that means that it is neither a reactant nor a product, but it's a catalyst, something that helps facilitate the reaction, helps it go faster, but it is not used up in the reaction, and at the end, that palladium in this example would emerge unchanged. When we witnessed the video about the decomposition of water, we were witnessing electrolysis. And to tell someone that you put electricity through the reaction, you put an E with a little negative sign above the arrow. Chemists are always looking for shorthands, so here's our shorthand version of the word heat. Rather than write the word heat, they put a little triangle up above the arrow. Now we haven't encountered them yet, but there are some reactions that can go forwards and backwards. So if, instead of seeing a single-headed arrow, you see a double arrow, one pointing left to right and one right to left, you're looking at a reversible reaction. And we'll consider those when we study equilibrium. It's a little bit on the large side, but that arrow that you can draw, as seen in number 11, is read as yields or produces. Another way to show the form of matter on number 12 and 13 is to draw an up arrow if you're producing a gaseous product, or a down arrow if one of your products is a solid precipitate. But I would like you to take a moment to make a note on this arrow and that one. You can only put those little down arrows to the bottom right of a substance on the product side. You can't use an up or down arrow on the reactant side. That's only for gases being given off or precipitates that are solid being formed. Stay on the right side of the produces arrow. Now those are most of the common symbols that you'll see. We learned in our demonstrations and also in our classroom activity with the equations that there are 5 reactions that you're going to need to understand. The first one, combustion reaction, obviously implies that something's on fire and it's giving off heat and light. You have to have oxygen to have a fire, and a very common type of combustion reaction is one when you burn a hydrocarbon, like acetylene. A hydrocarbon is any compound that is made of carbon and hydrogen, as you can see down here, the formula for acetylene, and maybe it might have oxygens and sometimes other substances. But bottom line is the only 2 products that you get are CO2 and water, and you see light energy being given off and you feel heat. That's a highly exothermic reaction. So that's one kind of a combustion reaction. There's our general equation. As you can see on the left is some kind of a hydrocarbon. You have to have oxygen on the left-hand side, and the only 2 products you get in complete combustion are carbon dioxide and water. Now, none of these videos are linked, so I'll be showing the videos with examples of combustion reactions in class. Now, another type of reaction that we learned about in our equations activity is a synthesis reaction, and that's easily recognizable. The hallmark recognition of it is only one product on the right-hand side, and it's a compound. Very important. Underline the words 2 or more. It doesn't just have to be 2 reactants on the left side. It can be any number of reactants, but on the right, you only make one product, and it has to be a compound. Synthesis reactions are also sometimes called composition reactions. And here's this lovely old car in a field of mustard, maybe, rusting away. It's a slow reaction. So here's iron reacting with oxygen to make iron oxide. You might want to ask yourself, is that car on fire? Just because there's oxygen on the left-hand side of a reactant doesn't mean that that's a combustion reaction. Iron and oxygen makes iron oxide, in this case iron 3 oxide. So sometimes when you see oxygen on the left, it might be a combustion reaction, but you use your common sense to tell you that rusting is not on fire. It's a slow oxidation process. So the hallmark of a synthesis reaction, as witnessed here in these 2 sample equations here, salt is the only product in reaction 1, and this calcium silicate is the only product of the second reaction. Synthesis or composition. And again, we already had seen this type of reaction, decomposition, or sometimes called dissociation, but decomposition is the better term, when you take one reactant and break it down into 2 or more. This time we have a compound, only one compound on the left, breaking down into the components that make it up. Now don't just get locked into thinking that it's 2 products on the right. It could be 3, 4, 5, but the hallmark feature is one compound on the left. And we've already witnessed the electrolysis of water video. So telling a decomposition from a composition is easy. Again, one compound on the left, two or more products are being produced on the right. Now there are two kinds of replacement, or sometimes called displacement reactions. The first one, called a single replacement reaction, is witnessed or observed when you see an element and a compound on the left trade places to make a new compound and free up another element. In this case, element A appears to be kicking out element B to form compound AC and free up a new version of element B. Element and compound on the left makes an element and a compound on the right, and it has to always be metals replace other metals and nonmetals replace other nonmetals. Let's look at an example of that. Here is iron in the form of this nail reacting with blue copper sulfate. Over time, brownish coppery stuff starts forming on the nail and the reaction looks less blue. That's because as iron reacts with copper sulfate, the iron will take the place of the copper, attach to the sulfate, and produce free copper. That's the gunky looking stuff that's forming on the nail. Notice that iron is a metal, copper is a metal, and metals can only ever replace other metals. So if you are trying to figure out how to write these equations as we get more adept at them, metals replace other metals. The iron could not take the place of the sulfate. Single replacement reactions are always going to be an element and a compound on the left make an element and the compound on the right. Notice in the second example, now the element that's on the left-hand side is a nonmetal. We will do a lab where this chlorine is going to try to replace either the potassium or the bromine. How do you know which one? If chlorine is a nonmetal, the only substance it can replace is the bromine, another nonmetal. Listen to how it sounds. Chlorine and potassium bromide make potassium chloride and bromine. Notice that when the elements of halogens go back to being pure elements, the "ide" sound turns into "ene." And an element in the compound on the left, another element and compound on the right. You can't miss a single displacement or replacement reaction. There is another type of reaction then that involves replacement, but we call this a double replacement reaction. I think of it as being analogous to two couples on the dance floor simultaneously cutting in on each other or trading partners. So AB and CD makes AD and BC. So a lot of times it's a reaction between ions of two different compounds that are in an aqueous solution, and one of those products can produce a precipitate. Not always. We will spend an entire lab and lots of equations to write representing double replacement or displacement reactions. Sometimes these are also called metathesis reactions. Again, as you look at these double replacement reactions, the only two that can trade places would be the lead takes the place of the potassium, or if you like to think of nonmetal replacing another nonmetal, you can do that as well. But the bottom line is lead nitrate and potassium iodide make lead iodide and potassium nitrate. And the yellow stuff you see forming here is the lead iodide, which is a solid. Can you think of another way to use a symbol besides a little letter S to show a precipitate? If you go back and look at your symbols chart, you will see the down arrow on the product side only is a good way to show the formation of a precipitate. Double replacement or double displacement equations are easily recognized. There are only two compounds on the left and two on the right. Now I hope you're beginning to see how important it was to learn your ions, because you can easily recognize hydrogen sulfate or sulfuric acid and lithium sulfate because you've memorized those polyatomic ions. Very important concept to be successful in chemistry this second semester. So we will show you an example in class of all of these basic types of reactions the next time that we get together. At the next time that we get together, we'll also learn how to do balancing. So at this point in time, you should readily be able to do your first worksheet, I believe it was page 15, on recognizing the 5 types of reactions that you are required to know. There are many other kinds of chemical reactions in chemistry, but for this class and this level, we'll stop with those 5. And I will see you at the next podcast.